Well, good morning, pre-calculus students. Hope everybody's doing well today. It's springtime, of course. You know, one of the things I enjoy, and good morning to everybody. Yes, hello, happy, as they say, happy Thursday. Uh, what I enjoy is looking at the forecast, and of course today it's going to be nice and balmy, like maybe 78, and then of course tomorrow it should rain a little bit, and the high is supposed to be maybe 55. So, so we get a real interesting mix of weather. So you know, this morning I'm running and it's like springtime, and then of course tomorrow it's going to feel like I'm in Montana. So only in Houston do we get this really interesting weather. Now, what I want to do today is start back with the quadratic functions and give a little bit more detail about those objects and do some examples. And also, as I've been working with students in the conference hours, it's really important that when you solve problems, like when you do your quizzes and you do your homework and for your first test, that you write down your work, because you will have to show your work that you will scan for the first test. And so just like I have solutions on the practice test, you do them in numeric order, and you show your work. You write down the equation, you solve the equation. If it's an inequality or a word problem, you set up the actual equation or inequality, and then you work it. The one phrase that I learned very much as an undergraduate, and also when I went back to grad school, an unsupported answer is a wrong answer. You don't look at a selection of answers and work backwards and say, oh, I figured it out. Well, no, you didn't. The idea is that you have to show me the mathematics and the work, if you have to set up variables. So all of that is extremely important. As a future STEM professional, you have to be able to work the problem analytically. Okay, this is not a standardized test where you're just trying to get in and get out and move on to the next question. This is a math class. This is a STEM math class. And so we write mathematics just like I do during lecture. So do keep that in mind as you work. I want you to grow in this class. I want you to get better. I want you to raise your standards so that when you get to calculus, you are ready to hit the ground running, so to speak. Okay, so let's get back to our quadratic functions and enjoy some interesting things about these particular objects. Now, like we had before, ladies and gentlemen, I wrote down some attributes yesterday about the vertex and things like that, where you have a maximum and a minimum, but I didn't really say anything about it. Like, you know, is there any reason why this might be the case? So let's delve into that. And then I want to do a fair amount of examples. This material is more complicated than what we did last class. That was fairly straightforward and actually pretty simple. But the quadratic functions offer a little bit more difficulty. So let's go back to that. So again, quadratic functions, and you're thinking when we get to conic sections, we will generalize the quadratic function and define the parabola. And that will be even more detailed that we'll get with these types of functions. It's going to be a lot of fun. So we defined f of x equals ax squared plus bx plus c. Now, of course, a, b, and c, we're going to deal with real numbers. Remember, using our notation, element of the real numbers. And of course, one thing that's extremely important is that we want our a to be non-zero, always. So when we work this, let me do the lighting just a little lower so it's not so washed out. There we go. And refocus. So we always want to make sure that we have a non-zero a so that we have a squared term. It could very well be the case that maybe b is 0 or possibly c is 0, and of course, as you will know, will simplify things, but we want a more generalized approach where we consider the a to be non-negative. So we always have the squared term. So it is definitely a quadratic function. So let's kind of look at this and say, okay, if we want a formula, I liked how some of you said, I like the formulas. Those are easy. So let's just see how we can get formulas if we actually complete the square. So our idea today, in this class, we really learn how to complete the square. And this is an important topic. And you'll use it in various places. In Cal 1, you'll sometimes use it more in Cal 2, but I want you to know how to do it and be comfortable with it. So what we're going to do first is we're going to factor the a from the first two terms, the x terms. And then, of course, just like we do when we factor doing problems, we'll have to compensate for factoring the a from the bx term by dividing by a. So like a 1 over a to absorb that. So that's the first step. And you're thinking, okay, so what's the deal here? Well, the idea is to create a perfect square. And I could have left a little room here, but I just want to kind of do these one step at a time. So all of the steps are very clear to you. Now, of course, this is where we could have left more room by the b over ax term to add the so-called magic number, but I just want to spread this out a little bit. So now we're going to write what we have, b over ax. What we're interested in doing is adding a constant term here that will complete the square, that will make a perfect square. Like when we say like a plus b quantity squared is a squared plus 2ab plus b squared, that's a perfect square with the binomial theorem. So what we want to do is see if we can accomplish that. And with quadratics, it's easy to do. So what we're going to do is we're going to take the coefficient of the x, which is b over a, and we're going to divide by 2. Now, a lot of times that just means multiply by 1/2, divide by 2. And then in order to make the perfect square formula work, we need to square this. So the divide by 2 is going to take care of that 2ab that we have in the expansion formula. And then, of course, remember, the second term has to be a square. So we take half of this coefficient and then we square it. And so this is b. I'll go ahead and write this as b over 2a quantity squared. Now we use our laws of exponents and we get b squared. And then, of course, we square the 2, we get a 4, and we square the a, and we get an a squared. So this is the completing square number. And it's the same every time you complete the square. If you have numbers, you think, okay, what's the number? Coefficient of x, take half of it, square it. Take half of it, square it. Always. That is the key. And what we do, for instance, we often rewrite equations. What do we do when we solve inequalities? We just chop away at them to make them so simple that we can figure out the solution. But each time we write an equivalent equation, we don't change the equation, we don't change the inequality, we rewrite it. So if this term here we can add to make a perfect square trinomial, if we add it, we must subtract it. So I'm going to write this in red. So b squared 4a squared, and then subtract it. So we're doing everything on one side of the equation. And then, of course, the c is over here by itself. Don't forget the c, it still counts. Now, like I said before, the process will never change. Now, one thing that's extremely important that I need to mention, in order to do this, the polynomial must have leading coefficient 1. That means monic. So you're thinking, why did we start out by factoring the A? I didn't make a big deal about that, but we need monic. What I mean by monic is that the leading coefficient, the coefficient of the squared term, is 1. That means monic, monic. We need monic. So when you complete the square, the first thing you have to do, if the coefficient of the x squared term or even the quadratic form term is not 1, you have to do it. So you will factor that particular coefficient from the squared term and the x term. Leave the constant term alone if it exists. So the idea is we get monic. From monic, we do the completing square term. Half, square it. And then, like I said before, if we add a term, we must subtract the term because we want these two equations to be equivalent, always. So here we get the so-called perfect square. And we can use our computation over here to write it. So this is ax plus b, that b over 2a, that's starting to look familiar, isn't it? Okay, b over 2a squared. So you don't have to believe Professor Ron, let's just do it. X squared, square this term, b squared, 4a squared, multiply these together, hit it with a 2, the 2 absorbs, and we get exactly that. So this technique will allow us to create a perfect square trinomial. So we say create a perfect square trinomial. Now, again, this isn't something that you have to do and remind yourself of every time. You remember the techniques, but I don't want you to think the technique is just some smoke and mirrors. Sometimes we'll use a result that we really can't prove because we don't have the calculus to prove it, but we can still use it. And that may be not as satisfying as what we're doing here, but unfortunately, that's the routine in mathematics sometimes. But we choose not to do that very often. Many times, you might have friends that take a statistics class, and there might be some really, really major theorems that they use in the class, which, of course, in the class they don't prove because they require higher methods of analysis. But the student can still use the result. So that's what we sometimes do in math, and it's not the most comforting, but it's a way to utilize a really important result and get some good out of it, get some reward out of it. Now, we've taken care of this part, and then we have the a times this straggling term. So let's write that down. So plus a, I'm not going to leave out any steps this time. Well, you know, I don't leave out steps, but I'm going to put in more steps so everybody's nice and comfortable. So this is what often happens. You put in the perfect square term here, but then you forget about what you had to subtract. But now remember, this is kind of like a term off to itself, a times this term right there. And notice one of the a's is going to absorb. So now we have a, and one thing I'm going to do, and this has become convention, we're going to put in 2 negatives to replace the plus. That's just convention. So that's where that negative b over 2a came from when I wrote that formula for the x coordinate of the vertex. Now we have a minus because we have a minus here, and certainly one of the a's will absorb. So this is kind of quasi-quadratic formula. Now at the very end, what we want to do is just get a common denominator for a. This is a 1 there. So we'll just do a common denominator of 4a, and we'll write the c term first. Of course, there's no 4a here, so we get 4ac minus b squared. Now you're thinking, well, look at all these formulas here. Look at all these formulas, but then you're thinking, oh, okay, that's the second form. That's the standard form number 2. Because now what is convention? You're thinking, wasn't that number the K, and wasn't that the H that you wrote before? Exactly. So what we do is we think, okay, the minus B over 2A, students can usually remember if they're trying to find the H. So convention will say A, this is why we put in the minus H quantity squared plus K, where, so again, remember, this is just plain old f of x, where H equals the negative B over 2A, and K is just this expression, which we don't really use, 4AC minus B squared over 4A. But you can just see that's just f of h. If you put in h for x, that annihilates this term, and you're just left with that. So that's why we can often write this as f of minus b over 2a. And that's the formula that I gave you last class. So that's why I could write these formulas here, where this defines the vertex, HK, vertex. So I wasn't making it up yesterday. I was just saying, okay, well, here's a recipe that we have for the quadratic function. And so now you're thinking, okay, I don't, I can think of it this way. If I'm going to work with a quadratic function, I can start with the first standard form, like here, ax squared plus bx plus c, and I can directly go to the x coordinate of the vertex by taking b divided by 2a and placing a negative on it. And then I can find the y coordinate of the vertex by evaluating the function at the h that we just computed right here. So f of h, or f of minus b over 2a. So that would be the standard form number 1 approach. Now, of course, you're thinking, I can use this, but I don't have to memorize anything. I can always complete the square. And depending on the form of the equation, it may be just as simple to complete the square. You just have to kind of pick the approach that you want to do. When I do some word problems, there will be instances where I'm going to show you new techniques that are very simple to do because we don't have a constant term. So you have plenty of flexibility here. So this completing the square tells you why this works. And so now we have the vertex and we have the axis of symmetry. The graph of the quadratic function will be symmetric relative to the vertical line that passes through the vertex, which is x equal h. This is the axis of symmetry. And then, of course, you're thinking, well, if we complete the square, that might make it a little bit easier to find x-intercepts, and we can compute, if they exist, compute x-intercepts. And then, of course, the y-intercept, which always exists unless we just restrict the domain. We usually don't. This will just be f of 0. So of course, the last thing has to do with the fact, and this is what we want to say a little bit about. I'll move this up because I still want to refer to the equation we have here. So you're thinking, okay, axis of symmetry, vertex. Why is the vertex so important? Why do we care? Why do we care about this point? What makes it so special? And then you're thinking, wait a minute. Professor Ron said something about maximum, minimum, and that must have something to do with it. So now, number one, I'll just say, why is the vertex V for vertex, H comma K. So a lot of times what we'll do is we'll label a point with a letter and then put the X and Y coordinates. I know that seems a little bit much, but that's sometimes standard. Why is the vertex important? Well, here's what we can do. First, let's assume that A is greater than 0. Now, if A is greater than 0, we can look at this term here and see that this term will always be non-negative. So this implies A x minus h squared is always non-negative. But then that just means, well, it's 0 when x is equal to h, but when x is not h, it's going to be positive. So this implies that these values can only get bigger. So this implies that k is the minimum value. That is, when x is equal to h, we just get k. And any other x we substitute will actually make the value of the function bigger because this will be a positive number. So this implies k is the minimum of f. And then you might be saying, oh, I get it. So if k is the minimum, then the vertex defines that point where the minimum occurs, and then the graph must open upward. So, and graph of f opens upward. And the shape, this is where we have to kind of rely on the fact that we do conic sections later when we define a parabola. Shape is a parabola. Now, of course, I haven't made a formal definition. That's like the U-shaped curve. When we get to conic sections, we'll formally define it and derive an equation for a parabola, which will be equivalent to this. But then we'll have extra in that not only can they open upward and downward, they'll be able to open left and right, which is kind of crazy, right? So we're seeing that these formulas aren't just there because someone decided, let's just kind of pick these out. They are distinguished. And now what about the other one? What about the maximum? 2. Suppose that the leading coefficient is negative. So this applies that this term here, this square term, x minus h quantity squared, is less than or equal to 0. So of course, when x is equal to h, you get 0. But of course, any other x you substitute, this will be positive, but then the a will make it less than 0. So the values of the function will start to drop. So again, this implies, just like in the first case, k is the maximum of f. So we get calculus without calculus. And we see that the completed square form gives us the calculus. So you can, for instance, you can just have a problem where it'll say, what's the maximum of this function? And then you're thinking, okay, well, that leading coefficient better be negative or this problem doesn't make any sense. So this says what? And graph of f opens downward. Now, of course, we don't get, any of the calculus otherwise, the concavity and the increasing, decreasing type thing. We kind of get that for free, but it's not specified in a calculus way. So you'll have to wait for calculus 1 for that. And again, the shape is a parabola. So when it comes to the quadratic function, there's really nothing that we don't know about it. And they occur often in calculus, in physics, in engineering, in finance. And so when you're doing a problem that involves a quadratic function or a function that has quadratic form, you can apply these techniques. And they make it very easy to maximize and minimize. Now, not every function is quadratic, clearly, but since they occur so much, it's like the exponential functions and the logarithmic functions. Why do we study them? Well, they're all over the place. Why do we study the trig functions, the sines and the cosines? Well, they're all over the place. We can't get away from them. And especially in STEM, they kind of form the bedrock of what you have to master before you do more work in physics and engineering. So let's look at some examples of this. Now, the idea here is, again, we have plenty of flexibility. A problem, for instance, if you're given one standard form, like the ax squared plus bx plus c, they'll say write in standard form. Well, that means the WebAssign wants the second form. Some students will just write the same form over, but clearly when you're asked to write a standard form, it would certainly be different from the one that was given to you. So don't fall into that pit where you're like, oh, I'm just going to be clever, and you just get the big X, so to speak. So I've got several examples here that I want to look at, and we're going to start with some simple ones. So here's an example, and then we'll do some word problems. So sometimes everybody just doesn't like the word problems. Just remember, they're just disguised equations and inequalities, no different. And don't be afraid of the numbers. The numbers will work with you if you just follow what they're telling you. So here we have a quadratic function. And we'll just kind of do everything we can to it just to kind of get used to these ideas. So we have a minus 5, x minus 2, quantity squared minus 5. So this is a, just go ahead and write this down. Excuse me. Running in the morning, all that dust, I'll be glad for some rain. But it's good. You can't have everything, right? So now, when you look at this, you're thinking, well, that's the, Professor Ron, that's the standard form number 2. And so when you think about it, let's just go ahead and remind us what that looked like. F of x equals a times x minus h, quantity squared, plus a k. And so now, one thing that's really important, we always need the minus here. So if there's a plus, we have to put in 2 minuses, because the h in this case will always be the number that is to the right of the minus. So if there's a plus, you have to insert the 2 minuses. And then of course the k here is whatever value it is. If it's minus, in this case, minus 5, k plus a negative 5, k is negative 5. So this one's easy to read, but we always need this one. We can always put in the plus negative 5. That's okay, that's easy. But here we do need the minus. So now what we can do is just kind of rewrite this in a form so it looks exactly like that. And put in the plus. Now that's kind of overkill, but now this matches up. So now we can see the number to the right of the negative in the square term is 2. So h equals 2. So we like the completed square form. And then we have plus k, so k is negative 5. And also a, which is the leading coefficient, equals negative 5, which is less than 0. So by our theorem, kind of a theorem, we didn't call it a theorem, but it is theorem, we say the maximum of f, you could say maximum value, or the maximum of f is negative 5. And then, of course, you can say, well, where does it occur? It occurs at x value 2. So you can say this corresponds to the vertex to negative 5. So remember, when you're looking for the maximum or the minimum, you're looking for the actual output. And so if you have a quadratic function where the leading coefficient is negative, the vertex will define the maximum, and it will be the k. Okay, so don't be very careful that when you actually answer it, that you put in a number, that you respond with a number, because the maximum or the minimum is a value of the function, the output. We often will write the ordered pair, for instance, just to show that the vertex defines the maximum or the minimum, because it will be the what? The y coordinate. And then, of course, it occurs at the h, the x coordinate. So again, it's one of those things where it's just a terminology game. Just be very careful that when you read the question, that if they ask for the vertex, you put the ordered pair. If they ask for the maximum, you put the value of k, and just follow the routine that is provided to you. Now, of course, we'll have axis of symmetry. Just go ahead and write everything down to get practice with this, because this, again, this is a lot more complicated than the inverse functions and the compositions. That was pretty simple. The transformations are not hard. You know how to do that, but this is more complicated. So now the axis of symmetry is just x equal h, x equal 2. And then we're thinking, okay, well, let's just see what else we can get. This is not in the best form, but we'll go ahead and get the y-intercept, and then we'll look for x-intercepts, y-intercept. So we want f of 0. So this will be negative 5, 0 minus 2 squared, minus 5. So this will give us a minus 5. Now, of course, we have a negative 2 squared. Remember, when we squared the negative, what happens to it? It absorbs. So I'll go ahead and write this down. Negative 2 squared minus 5. See, this is very important. All of you love the formulas, but if you get sloppy with the signs, the formulas won't get you where you want to go. So now remember, negative 2 times negative 2 is positive 4. So this is negative 5 times positive 4 minus 5. So this will be a negative 20 minus 5, which is negative 25. So the y-intercept is way down on the y-axis. This is the y-intercept. Remember, that's always defined to be f of 0. Now, of course, if we have the standard form number 1, that makes it easy. It's just the c, right? It's just the c. So when you've got the completed square form, you're thinking, man, this is not the way to go for the y-intercept. You have to do a lot more work because you've got more arithmetic to do. When it's in the standard form number 1, you just read it. It's like, boom, it's right in your face. Now, of course, so with that in mind, does the completed square form help you with the x-intercepts? And the answer is yes. So this means f of x equals 0. So when we find x-intercepts, we want to find when the output is actually 0. Does the graph cross the x-axis? Does the function have value output 0? So now let's do it. So we have -5 times x minus 2 quantity squared minus 5 equals 0. You can't work too much with the quadratic function theory. It's so useful. So now you're thinking, well, this is like section 1.5. Let's solve this. So we'll take the 5 over. So we have -5. And I think you know what the answer is going to be, but I didn't want to let the cat out of the bag. Just, go ahead and verify. So we add 5 to both sides. And now, if you will, we want to divide by -5. So let's do that. So we'll have x minus 2 squared equals 5. And of course, I divided that by -5, but I'll write this out just to make the point. 5 divided by -5 is -1. And now we look at this and say, okay, these values of x will not be real. Okay, we've got x minus 2 quantity squared equals a negative number. Okay, that's fine. We can apply the square root property, but we're going to get imaginary solutions. And of course, imaginary solutions don't show up in the real plane. So here we'll say no real solutions. And then you're thinking, well, that makes sense, Professor Ron, because the vertex is below the y-axis and it opens downward. I haven't written that, but it opens downward, so it's never going to hit the x-axis. So you could have thought, well, I don't need to do this. So as a little extra here, with this negative, graph opens downward. So we've got all these little ideas here that come into the discussion, which we may or may not need. But when you're doing a problem, you might have an example where WebAssign says, I want you to do everything. I want you to find all of this. Then I want you to give me a picture. So now when this says no real solutions, we can go back over here and say no x-intercepts. No x-intercepts. Again, no real solution, no x-intercept, not a surprise. And now what we can do, now here's another thing that I want to share with you. When you graph these things, you need a vertex, and then maybe you can use just a couple of other simple points to get 3 points total on the graph, because WebAssign usually likes 3 points when you're doing the quadratic function, just to, again, using your parabola tool, connecting your 3 points. And if the 3 points are correct, and when you connect them with the parabola tool, you'll get a check mark. So now let's go ahead and draw this. And I'll do it so we're spaced out a lot. And then of course I'll have to draw the scale. I have to have a fairly small scale on the y-axis. Don't worry if this doesn't look like Rembrandt. I mean, sometimes we're kind of stuck between a rock and a hard place. So here we've got what, 2, -5. So I'm going to mark off the y-axis in 5s. So 2, 3, 4, 5. So here's the -25. And here's the -5. Now, of course, on the x-axis, we can be a little bit more flexible and spread out a little bit more, which is fine. We won't have to be as crunched together. So we can do like a 1 and a 2. 1, 2. Like that. -1, -2. And then if you like, we can go ahead and get a value over here, 3, on either side of the axis of symmetry. So now what we can do, if you like, you can go ahead and draw in the axis of symmetry and the vertex. So the vertex will be 2, -5 right here. And then we can dot in So this will be x equals 2, which is the axis of symmetry. And now we can plot our y-intercept, which is negative 25 right here. Now, just for grins and, wanting to make this look good, we can go ahead and use the axis of symmetry. Let's figure out what f of 1 is. Now, of course, when we have the parabola, we can use the there's a term called the focal diameter. And the focal diameter, which we don't have for the standard quadratic function, makes finding extra points really simple, but we don't have that luxury now. So let's just get an extra point here, and we'll do like f of 1. So f of 1 will be a negative 5, 1 minus 2 squared minus 5. So this will be a negative 5, and of course that'll be a negative 1. In this case, 1 minus 2, so that'll be a negative 1 squared minus 5. So we get a negative 5. Again, the negative 1 times the negative 1 is 1 minus 5. So we get a minus 5 minus 5, which is a negative 10. So we've got, in this case, negative 10, about right here. And then we can use the axis of symmetry to go right on the other side and also get the 10. And then, of course, the idea is that we can use axis of symmetry here and move over 2 units. So let's go to 4 and get this point that corresponds here using the axis of symmetry. So we kind of get 2 for the price of 1, even though the scale is kind of bad. I've got that a little closer than I want, but again, this is not Rembrandt, obviously. So let's go ahead and connect. So what we see here is with the axis of symmetry, we kind of get 2 for the price of 1. We can get this point here and then go equidistant on the other side to get this point. So now what you can see is this point is 1, negative 10. And then we can go the same distance on the other side and get 3, negative 10. This point is, in this case, 0, negative 25, and we can go the same distance on the other side, 2 on the other side, and get 4, negative 25, using the axis of symmetry. And let me just write this point as an ordered pair, 0, negative 25. So again, this is not the focal diameter that we get with the parabola, which makes this a little bit easier. We can simply do the 2 for the price of 1. So when you're graphing a quadratic function, ladies and gentlemen, you always get the vertex. Now you might be thinking, if we got the x-intercepts, if they actually existed, that would be 2 points, 2 additional points there, but again, when you're using the graphing tool, it's better to get simple points if the intercepts are not nice numbers. So notice we got the y-intercept here. That gave us this point. So really, that probably would have been enough. And then, of course, I did an additional point here to show you how to use the axis of symmetry. So again, if you take a point that's a nice distance away from the x-coordinate of the vertex, then it's easy to move the same distance on the other side. So when you draw in the axis of symmetry, all it does is provide a guide to get additional points. So when you graph the parabola, make sure you've got at least 3 points. And that way, when you connect them, you'll get your check. Again, the idea is that when you're graphing a line, you need at least 2 points. When you're graphing a quadratic function, you need at least 3. So let's just kind of look at this and see how, when we work with any function that's quadratic, any function, it might be a word problem where maybe it doesn't make sense for X to be negative. Maybe we're doing like a business type problem where X is the number of units sold. So values that would be negative would, just be disregarded as not making any sense. So the idea is we can always do this with a quadratic function. We were blessed in this problem that we were given the completed square form, that is the standard form number 2, where we can directly read the h and the k. And then from there, we wrote down the axis of symmetry, the intercepts, and then with that information, we have a picture. So this is kind of like exhausting everything. We also got the maximum of the function. So this is like writing everything. And now the very last thing that you could do if you wanted to label, you could say vertex 2, -5. So if you can complete the square, if you like to do that, completing the square is not really that bad when you think about it, or use the formulas. If you can do these routines, which are fairly straightforward, then you can answer anything that you need to know about a quadratic function. So quadratic functions, excuse me, we completely understand. We have all the means to work with these. Unfortunately, when we get to degree 3, degree 4, and all that, it's gone. So we relish the fact that the quadratic function is our friend, because there's nothing that the quadratic function can keep from us. We can figure out what we need to know and move to the next level. Okay, excellent. So let's look at another one. So say, for instance, let's see here. Let's do an example where we actually get some intercepts that may not be the nicest numbers in the world. And let's see, here we go. So here, let's just do another free-for-all. That is, we're going to start with a quadratic function, and we're just going to completely analyze it. So when you're reviewing for a test, the best thing with quadratic functions is just to do this. I mean, really, and then I'll give you some additional techniques. So let's look at this. F of x equals 2x squared minus 4x minus 3. So this one's very different, at least in the way the packaging is. This is the standard form number 1. So this is what we're used to or accustomed to when we like maybe have a quadratic function or a quadratic equation, and then we try to factor and do the whole 9 yards with that. So again, this is a quadratic function. Quadratic function. Again, it has all the attributes, the square term. It has to have a square term, and it has a what? A linear term, a first degree term, and it also has a what? A constant term. Now we want to do this. I want to do the two steps here. I want to complete the square and get the vertex, and then use that, and then we'll use the formula so you can see all the options that you have with you. So now, when we look at this particular function, we see that it's not monic. When we did the derivation, the 2 is not a 1. So we want to factor the 2. And of course, these numbers are too nice, right? We wish we always had numbers this nice. So we have 2 x squared. Now, another thing, just to write this in a way that makes it easy, we're just going to say, okay, we have the -4, but in this case, I'm going to do it just like I did before. I'm just going to say divide by 2. I don't want you to guess. You can say, well, I can just factor the 2, Professor Ron. I know that's going to be a -2. No, just do it the same way every time. I mean, I know you can factor this, but before, maybe this turns out to be, 4/3 or something. And I don't want you to think, well, how do I do this? So now you're thinking, okay, well, that's just going to be a -2. So we have 2x squared minus 2x. So we had to pay for this. So even though, like I said, we would have done this naturally just to write this, maybe we would have thought about the derivation and saying that we have to pay for this. Fortunately, the 2 absorbs into the -4. And now we're thinking, okay, we need to do the completing square technique. So let's make a little bit of more space here. We have the -3. So we're thinking, wow, this is so much easier. Now we look at this and say, okay, let's do a little side calculation. We're going to do 1/2 times -2. And we want to square it. So again, this is -2 divided by 2 squared. This is -1 squared, which is 1. So all of the signs that we have to negotiate are just like what we talked about when we did even and odd functions. The negatives all running all over the place, and we do the same calculation. So again, the number that we must add here to complete the square to make the perfect square trinomial is 1. So we can say +1 -1. So I've got all this space here, a little bit more space than we needed. Okay. And so now here is the perfect square. So we have 2. And then of course we go over here to get the value that goes by the sign here, the minus. In this case, we get x minus 1 quantity squared. And then of course we have a 2 times a -1. So that's a -2. And then of course we have the -3 here. Now, of course, let's just check everything. Notice here, we do the x squared, we get x squared. We square the 1, we get the 1, and then the x times the -1 times 2 gives us -2x. So we did our calculation correctly. So now this equals, or if and only if, f of x equals 2 times x minus 1 quantity squared. And of course here, this is a -5, so we have -5. So let's go ahead and put it in the standard form with the plus. So 2x minus 1 quantity squared plus -5. So again, this is completing the square. Now again, why do I complete the square? I do this because you need to know how to do it. Okay, you really do need to know how to complete the square. And you did this in college algebra, I'm sure. Maybe not a lot, but you did. And if you didn't do it much or very little, then we really need to make sure you get it here. The technique, again, doesn't present itself every day, but when it does, it is extremely, extremely important. So now when we look at this, we're thinking, okay, well, our standard form, I'm always going to write this down just to remind you, number 2 is a x minus h quantity squared plus k. So we've got the minus here that we need. So h is 1 and k equals -5. So this corresponds to a vertex of 1, -5. And now we make the observation that A is positive. A equals 2, which is positive, which implies minimum of F is -5, the minimum. Again, when A is positive, the graph will open upward. And so the vertex will define the minimum. So we go to the K in this case, which is -5. So the minimum of F is -5. Really, you're thinking if this is the only question you have to ask, you can say, okay, if it's given this way, I'll do minus B over 2A, or I'll complete the square. Your choice. Now, just to kind of show you the other technique before we finish off the problem, let's just say that you decided, okay, you derived this, Professor Ron, I'm going to use it. You have from the first page, you got these nice formulas here. And you're thinking, okay, I'll use the formulas, maybe take a little less time. I don't know. I'll just try this out. So now, again, it's like doing the quadratic. It's exactly like doing the quadratic formula. We'll just do a little sidebar here. So we'll just say alternate. So here we have A equals 2 and B equals -4. Again, standard form number 1. So then H equals the opposite of B divided by 2A. So we have the negative of -4. This is where I look at students and say, whichever method you choose, be very careful with the signs because it's so easy to trip up. Again, so we have the additive inverse of the additive inverse of 4 divided by 2A. So this is 2 times 2. But of course, the additive inverse of the additive inverse absorbs the additive inverse. That's a theorem. So that's 4. And then of course, 2 times 2 is 4, and these absorb and we get 1, which is what we expected to get. So you might think, oh, okay, Professor Ron, I've just got to do minimum in this case. I'm going to do the formulas. And I'll say, yeah, probably a good way to do it. But again, I want you to know how to do this. And now you're thinking, okay, well, I need to find the minimum. So I need to evaluate the function at 1. So now we'll have K equals F of H, right? You don't have to remember that long-winded formula with the A's, B's, and C's. If you have H, you just evaluate F at H, and H is 1. So we get 2 times 1 squared minus 4 times 1 minus 3. So this will give us 1 squared, which is 1. So we get 2 minus 4 minus 3. So this is, if you like, this is what we'll just associate here. So this is -2 minus 3, which is -5. And again, that's exactly what we expected to get. So you pick the method based upon the problem. So this is what I'm talking about. When it comes to transformations, boom, boom, boom. Same thing every time. Inverses, solve for X, right? And then replace the X with the Y and graph them on the same set of axes, the domains and ranges flip. I mean, that's the same way every time. That is not complicated. Now, when you do the calculus of inverse functions, that'll be a little bit more complicated, but not a whole lot. So the idea here is that we have flexibility to the point that it's like, well, which one do I do? Or how do I do this or whatever? I'm not saying that everything is easy before this. I'm just saying that what we're doing now just requires that you make a lot of decisions that you're thinking, well, why doesn't the problem tell me what to do? Why are word problems hard? Well, basically because when you do a word problem, no one is saying, okay, be sure to set up the variable this way. And then if you have an ugly equation or inequality, neaten it up like Professor Ron does so you won't make mistakes. Well, no, the problem doesn't say that. That's why the word problems are difficult. They don't give you a roadmap. Okay, so now we've got the minimum, we've got the H and the K. Let's go ahead and finish off the problem. We can go ahead and write down the axis of symmetry. We have x equals 1 is the axis of symmetry. If we're asked to compute that, and now we want to go ahead and get the intercepts. This is where the standard form number 1 is easy for y-intercepts. So we just have f of 0. And that just means that the first two terms are annihilated and you just get the -3. So that's just a visual. That is, this just turns out to be the c. I'll just say, what does this equal? 2 times 0 squared minus 4 times 0 minus 3. 0 minus 0 minus 3. That's just kind of beating it up, but that's exactly what's going on. So when you do the y-intercept and you're saving time, it's like those 0 out, those are annihilated. The only thing that's left is the c. So this form is terrific for y-intercepts. Now, notice over here, we have a completed square form. And that's where, when it comes to doing x-intercepts, if you have the completed square form, it's much easier. So we're going to use that. Otherwise, you just use the quadratic formula. So x-intercepts. So we're going to take advantage of the fact that we know this. So this says f of x equals 0. So we've got 2 times x minus 1 quantity squared plus -5 equals 0. What is it, ladies and gentlemen? We just keep doing the same thing over and over. And then you think, why doesn't it get easier? Well, it does, but when you get to calculus, you're going to think you'll never do this again, but you're sorely mistaken. This is all you'll be doing. So get used to it and enjoy. So now we'll subtract or add 5 to both sides. So we get 2 times x minus 1 quantity squared equals 5. And now we're thinking, okay, well, we're going to get nice numbers here. In this particular case, we're going to get real solutions because we've got positives here. So if and only if x minus 1 quantity squared equals 5/2. And that's a positive number. So now we can apply the square root property. So x minus 1 equals plus or minus, and if you like, we'll just say the square root of 5/2. Now again, when we look at this, and it's your choice, we can leave it this way or we can try to clean it up a little bit. It doesn't matter. We'll just go ahead and we'll finish off the problem and then we'll clean it up a little bit. So x will be 1 plus or minus, and we can go ahead and write this as the square root of 5 over the square root of 2. So in this particular case, we're like, wow, look at these crazy numbers here. So when you look at this, you're thinking, well, can I make this look pretty? This is fine if WebAssign wants an exact answer, but let's make this look more beautiful if we wanted to maybe impress our friends. So we have x equals 1. Now we'll go ahead and get a common denominator. So we'll do square root 2. And so we'll have square root 2 plus or minus square root 5. Now at this point, you're thinking, okay, well, that's a little bit better, but they're still kind of unattractive numbers. So now if you wanted to make it look really nice, even though this is fine, you can multiply and divide by the square root of 2 to make that into a 2, if you like. Just a little bit of practice with rationalizing, just to give you some practice with it. So remember, this gives you that. So now we have x equals, so we'll do distributive law, square root of 2 times square root of 2. I'll do all the steps, plus or minus square root 5 times square root 2. And then, of course, now we'll have square root 2 times itself. So I thought this would be a good example just to do some additional work with radicals. And so now we have x equals, so we square the square root of 2, that's just 2, plus or minus square root 10, just say square root 5 times square root 2 is just square root of 5 times 2, so we get 10. And then downstairs we just get 2, square root 2. So this is a much more beautiful solution. And you're thinking, wow, got all these crazy numbers here, but this is just to make the solution look a little bit more user-friendly. It's not required, but it's user-friendly. And so now we can say, we can write it down. We have x equals 2 plus square root 10 over 2, or x equals 2 minus square root 10 over 2. Okay, so the beauty here is that you have two choices here. If we decided that we were going to go ahead and complete the square, we can use this formulation to solve for the actual x-intercepts here. But then we get some, unattractive radicals. Even though I am fine with this, there's nothing wrong with this. It's sometimes nicer to create a more user-friendly fraction. And so when in doing that, the first thing we do, like we did in section 4 of chapter 1, we get a common denominator of root 2. So we hit that with a root 2. Then we clean it up. We rationalize the denominator by multiplying and dividing by square root 2. And upon doing that, we get nice numbers. That is, we end up with a 2 plus or minus square root 10 divided by 2. Now, when you look at this, you're thinking, okay, now let's just do a ballpark approximation. Now, we can say square root of 9 is exactly 3. Square root of 10, we could just say, roughly 3.2 or whatever, just to make life simple. So we can say, okay, so now here is a, what we want to say, rough estimate. Now, of course, if you're doing your Google calculator, you can get a nice calculus estimate, which is, infinitely great. But just say, we're going to say that square root of 10, just to keep it simple, we'll say that's approximately 3.2. Then this is what we call a rough estimate. Then x equals 2 plus root 10 divided by 2 is approximately 2 plus 3.2 divided by 2. So this will be 5.2 divided by 2. And so now when you look at this, you can say, okay, well, I can go ahead and clean this up a little bit. Now, what I would recommend is maybe just getting rid of the fractions. So we'll say 52 over 20, multiply and divide by 10. And so here, when you divide by 2, or actually we can divide by 4, we get a 13. Divide by 4, we get a 5. So there's a rough estimate. And then, now there's a trick to getting this, but I'll just go ahead and work it out. X equals 2 minus square root 10 over 2 is approximately 2 minus 3.2 over 2. And so now we'll get the negative 1.2. So negative 3.2 plus 2 will give us a negative 1.2, and then multiply and divide by 10. Divide by 4, so we get negative 3/5. So those are some rough estimates of our x-intercepts. Now they're not calculus based, they're just rough estimates. And so sometimes a rough estimate, maybe you want a quick graph and you just want a rough estimate. Now, of course, if WebAssign asks you for an estimate, you go to your Google calculator, so it gives you a beautiful calculus estimate that you know, is really cheating, but you know, we live with it. So now we're thinking, what does this picture look like? So let's take all the stuff that we have and get a nice picture. So we've got our x-intercepts and oh, and we got the y-intercepts. So let's go ahead and draw this. And we've got a vertex of 1, -5. So I can spread this out a little bit. So we'll spread out the numbers a little bit so we can get a good picture. So for our vertex, I'll refer over here, come back over here. We have a vertex of 1, -5. So we'll spread this out a little bit. So we get 1, and then 1, 2, 3, 4. Living on the edge. Wow, it's spreading it out. There we go. Right there. So we have vertex 1, -5. And if you like, we can go ahead and dot in the axis of symmetry. This is just, again, giving you practice, working with the equations, working with the algebra. That's why I like to spend time on this, because this is what you do in calculus. And so this is x equals 1. And now, let's see, the y-intercept is -3. This was so much more user-friendly than the last one. We have a -3 right there. And then we have the x-intercepts, which again are going to be symmetrically distributed about the axis of symmetry. They have to be. And so we've got, let's go ahead and mark these off. This basically, this gives us what, 2 3/5. Well, and boom, right? So let's just, we got 2 and 3. So about right here, just a rough estimate. That's what we need when we're trying to get a picture. And then -3/5. So let's go ahead and connect. We got enough points. This is what you'd like to do on your test. You give me a nice picture. Okay. So now we've got our nice estimates here, but see the exact here, if we just wanted to point that out, the exact is 2 plus square root 10 over 2. We just write the coordinate pair. And then we have 2 minus square root 10 over 2, 0. Just to show that we have estimates of these. And then, of course, we have our y-intercept, which is just -3, but we'll write the actual ordered pair. And of course, we have our vertex. So the beauty of the quadratic function is that it just seems to never quit giving information. And what I want to point out here, ladies and gentlemen, is that this is not an easy construct. The quadratic function has complications that other things we've done do not have. I teach and continue to teach students that take the calculus that can't navigate the quadratic function. And it's not because they're incapable. It's just that they never ever put any time into it. So when you're working with quadratic functions, you've got to be able to navigate the algebra. You don't always get a packaged quadratic function that's user friendly. This one certainly isn't user-friendly. When you think about it, we get nice vertex, but the intercepts are not beautiful. I mean, we have them, and this would be kind of unfortunate in a calculus problem if you had these as limits of integration. So the idea is that when you hit this in calculus, you want to be able to navigate problems with quadratic functions with ease and competence. And we want to work our algebra and arithmetic in a very forthright way so that we can go back and check. And then, of course, as you're working your homework, you can do two methods. But when you take the test, if the method is not prescribed for you, then you use a method that you like. You use a method that gets you to the finish line. Now, what I want to do is some examples with some of the word problems. Now, there are all kinds of interesting problems here. Let me find this, and this was from your WebAssign. So let me find this problem. Yeah, here we go. So when you work physics and you work engineering, or some of you that are going to end up in finance on Wall Street, working for some big insurance company, or maybe you're going to work for the government. That would be a great career, a very rewarding career, but lots of challenge. So for instance, we have the following. Here's an example. Now, I want this to look like the last problem we did, in that we don't have to really construct anything. We're given a function, and then the light bulb has to come on that says, I think we know what to do. So in this particular case, we have, let's see, yes, X equals the number of units manufactured. So this will be the number of units manufactured. I used to teach some business calculus, and that is so much fun. You get all kinds of interesting problems, and boy, those kids, they learned the quadratic function. They had no choice. And we're given a revenue function. The revenue function, how much money you bring in, the revenue function for X, R of X, is given as follows. 80X, this reminds me of some of the problems I did yesterday in the office hours, the conference hours, 0.4 X squared. And then it says, compute the maximum revenue let me spell that correctly, compute the maximum revenue and number of units produced or units manufactured. So often when you have problems like this, you're thinking, okay, well, this is a problem you can do. First, you notice that the revenue function is quadratic. And so when someone says, okay, you've got a quadratic function, I want you to maximize it, the first thing that goes off in your mind is like, oh, okay, that leading coefficient better be less than 0 or this problem's inconsistent. And then you say, oh, okay, that's covered. And then it's like, oh, I need the vertex. Why is the vertex going to solve this problem? Well, not only will it give you the maximum, which is K, but it'll give you where it occurs, which is H. So you get the K and the H and you solve the problem. So in this case, solve by computing the vertex of R of X. So this is an example where I want to show you a technique that deals with the midpoint like you were working with the absolute value. That again makes the problem a little bit easier, but I'll let you be the judge of this. Most students try to do this with the minus b over 2a and mess it up. And I want to give you a technique that alludes to the factoring techniques I've already shown you. So here we go. Here's a new technique that borders on the fact that when you have x-intercepts, the midpoint of that segment is actually the what axis of symmetry, which we saw in the last problem, which automatically gives you h. So we've got r of x equals, we'll do this in descending order, 0.4 x squared minus 80x. Now, let's do a little sidebar here. 0.4 is, just write this with fractions, is 4 over 10, but that's just 2 over 5. So we're thinking, okay, well, we can factor this and use the fact that we don't even have a what? We don't even have a constant term. So we can find the midpoint of the intercept segments. So let's do it. So now this will give us negative 2/5 x squared minus 80x. And so now we're thinking zero product. We have an x in everything, so we can factor and use the zero product theorem. So let's factor. First, what we'll do is say, okay, well, we've got an x in both of these, and of course we want the leading coefficient of 1 to find the zeros, so we'll factor a negative 2/5 x. So negative 2/5 x. So of course that'll leave behind an x, that's the easy part. And then we have, let's go ahead and make this up. So we've got plus negative, in this case, 5 over 2. So when we think about this and we think about what we're doing, when we factor the negative here, 2/5, we want to pay for it here by multiplying by the reciprocal, and then that leaves us with what? The 80. Now, let's just make a comment here that will help us a little bit. When you look at this and you think about what we have here, you're thinking, okay, well, I've got to get my signs right, Professor Ron. So we've got a minus there. So let's check out and make sure this is correct. So when we factor this, we have the negative 80. We've taken out the x, and then we're paying for this. And so this is positive times the negative. So that gives us the negative here. So this requires a little bit more work in this case. Now, notice in this particular case that when we work this type of example, and we think about what we're doing, we're like, okay, so with this particular type of problem, how are the intercepts going to help us? Well, let's just go ahead and finish this off. So we have negative 2/5, and then we have an x. Now, at this particular case, we look at this and say, okay, well, this gives us, again, a plus. So we've got a plus. So we have an 80 over 2 times a 5. And now when we look at this, this will give us a negative 2/5. Of course, I've got an x here. I left my x out. Sorry about that. And now we've got an x plus. Now this will give us a 40 times a 5. So we get negative 2/5 x times an x plus, in this case, a 200. Now, let's just check everything and make sure all of this looks right. And I want to make sure that this makes sense to you, because this is a good technique. When you look at this, the first thing we do is we write the decimal as a fraction, which is 2/5. And notice here, when I wrote this original problem, this is what I noticed when I did this. This is a plus here. And so when I was working this, I thought, well, they'll see that I didn't write the correct sign for the 80, but that's okay. That you all are good kids. You just say, well, Professor Ron knows what he's doing. So let's just put the plus in here. So here's the plus. So we get the minus. How funny. You all are good kids. But the math has to tell us the correct story. So when I wrote this down, when I transferred it, or when I transposed it, I didn't put my plus here. So we always have to be vigilant, because I looked at it and I said, well, I'm not getting the right sign because I didn't do this. So this is why you have to write everything down. Now, set this equal to 0. So this is if and only if x equals 0, which is this factor here, or x equals 200. So these are the x-intercepts, which now will be bisected by the axis of symmetry. So now we say h equals the midpoint, in this case, of here, we've done this before, 0 plus 200 over 2, which is 200 over 2, which is 100. So this is the x-coordinate of the vertex. And now we can get r just by doing the substitution into our completed square form. So now k is r of 100. Just substitute here, -2/5 times 100 times 100 minus 200. These numbers are so easy, it's worth the trouble. That's just a big mess. And so now 5 will divide the 100 20 times. So we get -2 times 20 times a -100. So this gives us a -40 times -100, negative times a negative, 4,000. So this implies max revenue is 4,000 with 100 units manufactured. Now, of course, the other approach is to say just do minus b over 2a and solve for that, for k, by substituting h into r, which is fine. But what's so nice about this is that it gives you a way to think about all the graphs we've done and think about the x-intercepts in a way that provides a very simple analysis. So the thing here is that you introduce an equation that's simple to evaluate, has no decimals in it, very easy to evaluate, and very simple to check. Because of course, you know, now here it's like I had a plus here and it's like, wait a minute, I had an error when I wrote this, the equation here. And so it's easy to self-check and you don't have to guess. Now, here's another example, just like this one, or with a similar technique. Know how to do this. This is important. The other example, I thought this was interesting, has to do with, again, another production example. And then there's one about a corral, a rectangular corral. I'll let you look at that one. We might have time to work on it. So here we've got a production problem. It says if n trees, n is a variable, n trees are planted per acre, then each tree produces, so this is kind of like a density problem. When you have n trees are planted per acre, then each tree produces 1,900 minus 19n apples. So you've got some biologists and some agricultural experts with data. Then it says, this implies the number of apples produced per acre is what? Well, it's just the number of trees times the production per tree. So we're going to call this A of N. Call it P of N for production if you want, just A of N. WebAssign uses A of N. Will now be N, the number of trees per acre, times the production per tree. And then it asks the following: compute the number of trees to be planted to maximize the yield per acre. So maximize the yield per acre by computing the optimal N. And then just for grins, we'll just go ahead and compute the production per acre. Now, again, WebAssign describes the problem this way. They don't even make you compute this. They just say, well, here is the production per tree. And if you have N trees per acre, then the N times the production per tree will give you the production per acre. That is, the number of apples produced per acre is just this. Well, this looks just like the last problem, but even better. It's already set up for us, basically. So the idea is that you're thinking, well, I'm going to multiply all this out and do minus B over 2A. No, you don't have to do that. You're going to use the same technique I taught you in the last problem. So now notice this is already zero product, but we can go ahead and clean up this factor to make it a little bit easier to figure out the zeros. So now, again, compute the vertex. These are some of the most important problems you do in the review part, even though this isn't really review from college algebra. These problems are too complicated for college algebra. So that's why you do them in pre-calculus. So now you're thinking, all right, let's go ahead and clean this up. A of N, we've got an N here, and we're going to go ahead and turn this around, and I'll remember to put the plus here. The beautiful thing about mathematics is that every step can be verified, and that's what is beautiful about it. You can always adjust and verify. So now you're thinking we want a leading coefficient here of 1, so we'll factor the negative 19. So this will be a negative 19n. The n's already out there, so that leaves us with an n. And now we have plus negative 1 over 19 times 1900. So again, we're paying for the fact that we factored the negative 19 from both of these. And I'm using the same technique I used before. And of course, the negative 19 or the 19 will absorb into this, which is fine. So use the same technique, don't guess. So this gives us negative 19n. So we have n, and of course we've got the minus 19 into 19, that'll give us the 1 and 2 zeros, so we get minus 100. So now we've got the same setup that we had before with the revenue. Set this to 0 to get the x-intercepts. If and only if, so we'll get n equals 0 from this factor, or from this factor, n equals 100. So when you think about the axis of symmetry, bisecting the segment formed by the x-intercepts, then you got a very simple problem. And these are set up to give you nice integer solutions. So you don't have to work very hard. So now midpoint of the x-intercepts will be 0 plus 100 over 2, which is 100 over 2, which is 50. So that's the optimal n. That is, this implies, and this is important, plant plant 50 trees per acre. The old story about the businessman who owns the hotel. How do you make the most money? You certainly don't make the most money when the hotel is full, no vacancy. You go into the hole. There's an optimal number of occupants that will equalize everything. When you have to consider how much it costs to run the place, pay for utilities, pay for your staff, having a full house is not what you want all the time. So the mathematics can be very deceptive. But when you look at this, we take what the biologist and the agricultural engineers decided upon, and then we see, oh, okay, we've got a nice quadratic equation. So let's see here, we've got a chat. Let me move Professor Ron. Well, I don't see it, so let's just see here. Okay, well, it disappeared. I guess everybody answered that question. So now we're thinking, okay, how do we get the maximum output? What's the output in this case? How many apples do we get? Well, let's just do the computation. So now, maximum output. And this just gives us A of 50, and I'll be able to set up that other problem. So we get 50. And in this case, notice here, we can use either one of these. We can use the original, or we can use this. Let's just see what we have here. This one will be a little bit simpler. Let's just use that one. Let's use the one that's the most tidy. So we'll just use this one. So we have negative 19 times 50, and then 50 minus 100. So that's just negative 50. So in this case, if you like, this will be, we're going to go ahead and factor both of the negatives. So this will be a negative 19 times 50 times the negative 50. So two negatives are positive. So this gives us 19 times, and that'll be 2,500. So 50 times 50 is 2,500. And here's a trick we can use. We'll just say 20 minus 1 times 2,500. To re-express the 19 as two simpler summands. So this will be 20 times 2,500 minus 2,500. So this is easy to compute. When we do 2 times 25, that's a 50. So we have 50 and 1, 2, 3 zeros minus 2,500. And that'll just give us what? 47.5, right? That's easy to subtract. So we can get that many apples when we plant 50 trees per acre. So the beauty of the quadratic function is that you have options. And I want you to explore this. You can use whatever you want, but if it comes to us in this form where we don't have a constant term, we can simply just look at the midpoint. So this is a technique that will be useful and you will see again. And I actually taught this and developed this when I taught business calculus, because they had this all the time and they always messed up the minus b over 2a. They could do this though. I taught them how to factor. They could factor and they said, Professor Ron, we can factor. So we're going to do this. So good for them and good for you. Now, the very last one is about the corral. Let's see. Yes. Got this right here. We have time for it, so we'll go ahead and do it. So in this case, it's like there is 1,400 feet of fencing, 1,400 feet of fencing to make a rectangular corral. So this is really a simple problem. And here's how it goes. It says, find the dimensions of the rectangle that maximize the area of the corral. That's all we need to solve this problem. So find the dimensions of the rectangle that maximize the area of the corral. And you're thinking, well, that's easy. The problems we had before gave us the functions, but these functions are easy because we can use perimeter. So say, for instance, you can just draw your rectangular corral. And if you like, you can just specify one dimension to be X and the other dimension to be Y. And this is where we get to use perimeter. So this implies that 2x, this is like the problem with the painting and the border, similar, but not nearly as long-winded. 2x plus 2y equals 1400. So these numbers are nice to us. And so, of course, we can factor the 2 because we're lazy. And now divide each side by 2. So we get x plus y equals 1400 over 2. Well, nice simple arithmetic. All the arithmetic we've had today hasn't been that simple. But now we can solve for y in terms of x. Y equals 700 minus x. So now it's like, okay, we have x as the dimension here, and then of course y, if we have this much fencing, will be the dimension here. And you're thinking, how simple is this? Professor Ron, we love these problems. They're so easy. The reason I wanted to end with this is that now you can see this technique I've been developing is really the way to go, especially when you don't have a constant term. Now, of course, if you have a constant term, then you can deal with the completing the square or do the minus b over 2a. But now we define area of corral as, if you like, a of x will just be length times width. So it'll be x times y, x 700 minus x. And you're thinking, how simple is this? So when we think of the last problem, again, that's basically what we got here, but even easier. So now if you want, you can factor the negative. So this will, and just first turn it around and then factor the negative. So we get x minus 700. So now we've set up for the, again, negative x squared. And in this case, let's see, oh, here, do it this way. Just factor the negative, not there's no x to factor. Forgive me, just factor the negative. There we go, that looks a little bit better. So now this is set up for zero factor. It's so simple, it's like, it's hard. So now when we set this equal to 0, we get x equals 0 or x equals 700. So this one gives us the 0. This one gives us the 700. So this is actually very, very simple if you use the factoring techniques I've taught you. But this, like I say, this is so simple, it's like in our face. So now midpoint, H, will be midpoint. So we have 0 plus 700 divided by 2. So this is 700 over 2. Okay, that'll be what, 35? 35 with a 0? And so now, so this is X or H. Then Y is just 700 minus 350, again, which is what? 350. So it's not surprising that the rectangle of maximum area is actually a square. That's a calculus problem. But we don't need calculus to do this because the quadratic function provides the calculus for free. So now we're seeing is that the corral of maximum area has dimensions 350 feet by 350 feet. So the interesting thing here, and then of course in this problem, it just says, it just find the dimensions. And then of course, if you just multiply this out, well, let's just finish it off. Why not? You know, maybe we're working for the FBI and they just docked our salary because we didn't finish the problem. So now it's like, okay, so if those are the dimensions, what's the area? Okay, so we have A of X. Let's just write down what we have from here. Bring this down a little bit. A of X equals negative X times X minus 700. That's just that factored version. So A of 350 will be negative 350, and then 350 minus 700. Use any form you like, but of course this will just be negative 350 times what? Negative 350. And of course the negatives absorb. So this, and when you look at this, you're thinking, well, we can use the binomial theorem for this. So this is just 350 squared. And we can write this as, let's do it this way. Let's just practice the binomial theorem. 300 plus 50, or you could just do 35 squared and tack on the zeros, but this will just be good practice. Let's just do 350 plus 50 quantity squared. So this will give us 300 squared plus 2 times 300 times 50, binomial theorem, plus 50 squared. So this gives us some practice with our identities, so to speak. And so now this will be a 9 with 4 zeros, 1, 2, 3, 4, plus, so we have 2, and now we get 3 zeros. That's 15,015 with 3 zeros. Yeah, let me put just one dot there. And then of course here, this will be a 25 with 2 zeros. So this gives us 90,000 plus 30,000 plus 2,500. And so of course, when we add this, that gives us 120,000 plus 2,500. So these will just run right in here. We don't even have to do any work. 1, 2, 2, 5, 0, 0. So when you're doing these problems, the level of analysis really transcends to factoring and dealing with the requisite arithmetic. So what I want to point out here is that when it comes to quadratic functions, you have tremendous flexibility. But when you don't have a constant term, you can simply use this midpoint technique. And again, we had this famous problem, remember? Remember when we graphed this? This is kind of what opened the door to the fact that this creates a nice geometry here. The x-intercepts provide a way to find the h by simply doing the midpoint of the segment created by them. That is part of the mathematics. And so when you're dealing with, in this case, quadratic functions, you have that geometry to work with. Now, again, as you work through these problems, you have many, many methods to work with. But when you have something this simple and you can do this technique, it's very easy. So when you solve these problems on the test, it does not matter about the technique. It would be very nice if you've got a word problem that utilizes this technique. That would be a very nice way to solve the problem. But whatever answer that you find, there must be some legitimate mathematics to support it. And so you have many options. So you can complete the square, which would be crazy here. You can use the midpoint technique, or you can use the minus b over 2a. So you've got basically three choices. But I think the mathematics here with the midpoint is so unique. And when you think about the curves, you can draw your curves with all of these problems. You get that nice curve that opens downward, and you've got those two x-intercepts that make sense in the problem. So again, when you are doing your work for the first test and completing everything, this will be the last topic. So the Blackboard announcement that I made for the first test, we start with 1.3 and we move through compositions, inverses, and then quadratic functions. Now, whatever we cover next week will not be on the test, but the actual material for test one ends today. And let me just also remind you, when you, and this I'll remind you with some other Blackboard announcements, when you scan your papers, it's like, for instance, say, you did this work and here's Professor Ron just took his test. You will scan each of your pages and you will combine that into one file. I would prefer a PDF. That way I can scroll through your work and keep everything in numeric order. And so I would scan these pages and create one file, and then I'll go to test one work, and that'll be the Turnitin function that you'll use, and you'll upload one file. You must upload one file. That is, you can't give me a bunch of pictures of here and there and whatever. So you've got to be able to scan this and produce one file. So use your favorite software. I mean, there are lots of free softwares. I like the Adobe software, but of course I have an Adobe account, a personal account, but there are certainly many softwares that you can find at the iStore and the Google Store that allow you to scan to PDF, and that way you make one nice file. And then that file comes right to Blackboard, right to Professor Ron. And when I look at your test on Blackboard, I'll go straight to your work and verify that you've done your work. So just remember, an unsupported answer is a wrong answer. If you do not support your work with relevant mathematics, it's not correct. And when I work out a problem, I work it out in complete detail. As you look at the SmartPen videos, as you look at the lectures, as you look at the practice test with solutions, you know exactly what I'm expecting. So again, I appreciate your attendance today. Like I said before, we're experiencing the summertime weather, the spring weather, but tomorrow it's going to be cold again. So that'll keep us on our toes. But with that said, if you go out, make sure you're safe with the mask and wrap up. Of course, when I run in the morning, I'll have to wrap up my Dr. Phil head because otherwise I'll get sick. So I appreciate your time today. And just remember, I've got 3 sessions today. This day never ends. I'll send out email invitations for all of those. We've got the early session, the afternoon session, and then I have the evening session. And then of course I have another session tomorrow morning. So please take advantage of these to kind of get yourself set up for what's to come. So again, thank you for your attendance today. I hope you enjoy the quadratic functions. It's one of my favorite topics. It's like teaching trigonometry. That's the funnest thing because I love Fourier analysis. But you all have a great day, and I look forward to seeing you at the conference hours. If not, I'll see you the next time we have lecture. Everybody have a great one.